So here is the first one we're gonna look at, which is XGBoost in H2O. Guess what? We're importing the HGO XGBoost estimator. First we did the linear estimator, then we did the random forest estimator, we did XGBoost estimator. I would love for you to look at all the different kind of models they have in there and to try some out that we haven't used for your final assignment. This is the boring bit. We do it. Even with containers, it's possible to be sloppy and run different versions of the containers, which have different versions of pandas. If you then pickle a data set with one version of pandas, you can't necessarily unpickle it with another version of pandas, which is what I just found out the hard way. Let's carry on. Start our session, send data to H2O. And here we go, 1XGBoost model. What do we have? Number of trees, 200. Is that going to be enough? Depends on the learning rate. The slower the learning rate in your gradient descent, the more steps you need to get to the correct position. You should remember that from week number 1. This is very different to random forests, where each tree is a full model, and all we're trying to do is averaging, and all we're trying to do is to average out the errors, and it seems to take a few hundred trees to average out the errors. You could easily find, if you have your learning rate low enough, that you need something like 2,000 trees or 10,000 trees max depth, as opposed to random forests where we need each tree to have no bias, so that when we take the averages of the models, we just get rid of the variance and the bias-free models are there for us, and we therefore have an amazing average. That's for random forests, so each tree needs to be complicated in a random forest. In gradient boosting, we are taking little steps, and each step doesn't have to be complicated. It's the sum of the steps that has to be complicated. And for sure, you will find that whereas random forests typically have trees in them with a depth of 20, the typical depth people use for the trees in gradient boosting machines are probably between 4 and 7. The sample rate, same again as we had last time. This is the proportion of examples that get used in each tree, and likewise called sample rate per tree. Now, why in gradient boosting would we think that we needed to add randomness? We understood in random forest that we're trying to get the noise to point in different directions so that it cancels itself out. But in gradient boosting machines, where it's just about having a complicated enough function and moving a little step in that direction and then doing it again, why do we need the functions to pick up different parts of the data? That is a good question. I don't know theoretically why we need that, but these parameters are available to us and we should tune them. Minimum rows 10. You shouldn't underestimate this parameter. You might have a data set with a few million records, and you could usefully set minimum rows to 100 or 200 or even 300 and still get very good results, and possibly get better results than having minimum rows stupidly low, like we do over here. We're going to go for early stopping again. I think I've explained that before. If performance doesn't improve after 20 trees, H2O will just stop growing it for us. And then the rest is the same. Model.train, model.predict. How rubbish is that? High validation error, massive overfitting. What do you think we need to do? You should already be able to guess. What can we do to get rid of the overfitting? Increase the minimum rows is one possibility. Reduce the learning rate and have more trees so that it's hopefully not paying so much attention to the noise coming out of the individual trees. Reduce the max depth. Now, one question, do we need more trees? Well, that's really easy. We're just going to plot the performance of this ensemble of little trees as we add extra trees to it. I hope it's clear to you from this diagram that we do need more trees. At 200 trees, both training and validation curves are still going down. There's no sign that we've reached any kind of optimum point, so we also need more trees. So we're going to do the same random grid search with the same code that I used last time. I don't recommend it. Get a proper random grid search going for yourself if that's what you use, and get it going with the H2O grid search so you can use it on multiple cores. We're going to check out a few different depths, 5, 6, 7, 8, 9, sample rate, see if that makes a difference. Minimum rows, 2, 5, 10, 20, 40. I reckon we should have 80 in there as well, but I don't. Set up a data set, shuffle it, fit 20 models, and here we go. I'm just going to pause the video while it chugs through that. Okay, that's it. 20 models have run. Drop the NA ones, the ones we didn't actually fit. And of the remaining ones, find the best performance. Once again, we've got massive overfitting. Train MAE 7,000, validation 14,000. What can we do about that? Last time I ran this, max depth that came out was 7, and what I then did, I looked at all the max depth 7 results, and I found that MinRes 10 was much better in terms of less overfitting, and I therefore chose max depth 7, MinRes 10. So let's do that again this time. That is pretty horrid. We still have a big difference. I can see that last time I increased the leaf size to 20. I'm going to do that again quickly. That's interesting. I just increased the leaf size to 40, or the min rows to 40, and I'm now finally getting some semi-decent results. I've got a test error not much worse than the one I had last time I did it. The overfitting is still pretty horrid. It's strange, really, really strange. These are pretty much the same scripts that I ran last year. I tried to be careful about reproducibility, but you can see here that I've completely and utterly failed. Maybe that's why I make such a fuss about it when you're doing your work. Who knows? What do we see so far about XGBoost? Well, it's really fiddly to tune these hyperparameters, and I've only tried tuning 3 of them in my grid search. How would you tune all of them? And even if you do run quite a large grid search, you've got to be careful about overfitting, because the best validation error might have opened up a huge difference between train and val, and that suggests that you're getting that validation error at a cost of a massive amount of variance, and that will probably hurt when you look at test data that your model has never seen before. What can we do? Well, you can train quite a big grid, and then you can select from that grid, but only where the difference between train and validation is not too huge. The alternative is to use a package specially built to tune hyperparameters. Now, one of them is called HyperOpt. We're going to see it, I think, in one of the next 2 workbooks. I'm not sure that I've really got time to go into gory detail with you about it, but there is a tutorial which I'm going to point you towards. Anyway, that's it for H2O and XGBoost. The basics of it, I hope you find they're pretty simple, because it's the same as always. Import the model class, fit the model using whatever parameters you can find in the help, do some kind of grid search to optimize those parameters, dot predict, see where you are, and that's really it.